Hello everyone, I welcome you in lecture number 2 on eigenvalues and eigenvectors. In this lecture we will discuss example on how to find out eigenvalues and eigenvectors of a square matrix. Before going for the examples, we understand this remark or not. Suppose we have polynomial equation of this type, lambda raised to n plus c1 lambda raised to n minus 1 and so on plus cn equal to 0, where these coefficients c1, c2, cn are integers. c1, c2, cn are constants, but here we restrict that these coefficients are integer. Then if there is any integer solution of this equation 1, or if there is any value of lambda which is integer and which satisfy this equation 1, then that integer solution must be divisor of this constant term cn. So all integer solutions, if there are any, to a polynomial equation 1 with integer coefficients must be divisors of the constant term. So if we have this type of polynomial equation in which all the coefficients are integers, then if there is any integer solution of this equation 1, then it must be a divisor of this constant term. For example, we know that lambda equal to 2 and minus 2 are solutions of this equation. This is a polynomial equation of degree 2. So here coefficients are integers. Coefficient of lambda square is 1. Coefficient of lambda raised to 0, that is constant term, which is also integer. So as per this note, if there is any value of lambda which is integer and which satisfy this equation, then it must be divisor of this constant term minus 4, and we know that the solutions of these equations are 2 and minus 2, and both are divisors of this minus 4. So if we have polynomial equation of degree greater than 2, then this will be useful to determine the solutions. If I have this equation, say lambda square plus 9 equal to 0, then this is also a polynomial equation of degree 2 with integer coefficients. So if there is any integer solution, then it must be divisor of constant term 9. Now divisors of constant term are plus or minus 1, plus or minus 3 and plus or minus 9. These are the divisors of the constant term 9. So if there is any value of lambda which is integer and satisfy this equation, then it must be from these 6 values. If these values do not satisfy this equation, it means that this equation has no integer solution. So we can check by putting these values in this equation, and we will find that no value of these 6 values satisfy this equation. So there is no integer solution for this equation, because if there is any integer solution, then it must be a divisor of constant term 9. So after putting these values here, we find that no value satisfy this equation. Therefore this equation has no integer solution. So whenever we have this type of polynomial equation, and if coefficients are integers, then we can use this note to decide the roots of this equation. We understand with another example. We consider this polynomial equation of degree 3, lambda cube minus 8 lambda square plus 17 lambda minus 4 equal to 0. Here all the coefficients are constant, integers, 1, minus 8, 17, minus 4. So this is a polynomial equation with integer coefficients. So if there is any integer solution to this equation, then it will be a divisor of constant term, which is minus 4, and divisors of minus 4 are plus or minus 1, plus or minus 2, and plus or minus 4. So we can put all these divisors one by one. Suppose we put lambda equal to 1, we have 1 minus 8 plus 17 minus 4. So this is going to be 18 minus 12, which is 6, and it is non-zero. That means lambda equal to 1 is not the solution of this equation. Now we check for lambda equal to minus 1. So for lambda equal to minus 1, we have minus 1 cube. Here lambda square minus 1 square, that is 1, plus 17 into minus 1. So this is going to be minus 17 and minus 4. And we can see here also we are getting non-zero value. This is minus 9, 9 plus 7, minus 26, and minus 4, which is minus 30. So it is non-zero. So these two are not solutions of this equation. Similarly, you can check for lambda equal to 2 minus 4, 4 minus 4, and after putting all these values, we find that lambda equal to 4 is an integer solution of this equation. If we put lambda equal to 4, we have 4 cube, that is 64, minus 8 into 4 square, that is 16, plus 17 into 4 minus 4. So this is going to be 64 minus 16 into 8, which is 128. This is 17 into 4, which is 68, and minus 4. And this is going to be 64 plus 64, which is 128 minus 128. So lambda equal to 4 satisfies this equation. So therefore lambda equal to 4 is the solution of this equation. So we observe that this is a polynomial equation with integer coefficients. Therefore we are trying the divisors of minus 4 for integer solutions, and we find that lambda equal to 4 satisfies this equation. So lambda equal to 4 is one solution of this equation. Now to find out another solutions, we know that if lambda equal to 4 is a solution of this equation, then one factor of this left hand side will be lambda minus 4, and another factor will be a polynomial of second degree that we can find using method of synthetic division. So here we have written, therefore lambda minus 4 must be a factor of the left hand side of given equation. So this equation is nothing but lambda minus 4 times another polynomial of second degree. So that polynomial we can find using method of synthetic division. Here we write down one root which we have obtained, that is 4, and here we have written coefficients of powers of lambda from this. Here coefficient of lambda cube 1, then minus 8, 17, and minus 4. We will write here 0 always, and we add these two. So 1 plus 0 is 1, and whatever we obtain here, that will be multiplied with this 4, and we obtain 4 here. So after multiplying this by 4, whatever we obtain, that we write here, and then again we add these two. So minus 8 plus 4, which is minus 4, that is multiplied with 4, which is minus 16, and it is written here, and again we add these two. 17 plus minus 16, which is 1, that is multiplied with 4, and 4 is written here. Now if this is the coefficient of lambda cube, here we will decrease one power, So we will start with lambda square. So 1 into lambda square, which is lambda square, minus 4 into lambda, which is minus 4 lambda, and plus constant term, which is 1. So second factor we can find in this way. So therefore we put that values here. Left hand side is replaced by lambda minus 4 into that quadratic factor equal to 0. So therefore equation 2 becomes lambda minus 4 into lambda square minus 4 lambda plus 1 equal to 0. Here also we can check. This is a polynomial in which all the coefficients are integers. So if there is any integer solution, then it must be a divisor of 1. That is, either integer solution is 1 or minus 1. For this factor, because it is a polynomial with integer coefficients, if there is any integer solution to this equation, then it must be a divisor of constant term, which is 1 here. So if we put lambda equal to 1, we obtain non-zero, and if we put lambda equal to minus 1, then also it is non-zero. So that means this equation has no integer solution. For quadratic equation, it is not necessary to apply this logic, but this is just to understand that remark. Otherwise, for quadratic equation, we will use this formula of solving quadratic equation. Solution of this quadratic equation is given by minus b plus or minus square root of b square minus 4ac divided by 2a. So here we find out value of lambda using this formula. So here b is minus 4. So minus b is 4 plus or minus square root of minus 4 square, which is 16, minus 4 into coefficient of lambda square into constant term divided by 2 into coefficient of lambda square. Here we obtain 16 minus 4, that is 12. 12 can be written as square root of 4 into 3, that is 2 under root 3. So here we replace square root of 12 by 2 under root 3, and we can cancel out this 2 by taking 2 common from the numerator. So we obtain these values. So lambda equal to 4 and lambda equal to 2 plus or minus root 3 are solutions of this polynomial equation. So whenever we have degree of polynomial equation bigger than 2, then this remark will be helpful. If there is any integer solution to this polynomial equation with integer coefficients, then that integer solution must be a divisor of the constant term. So by trial and error we will be able to find out one value of lambda by taking different divisors of constant term. And if no divisor of constant term satisfies this equation, that means this equation has no integer solution. Now we consider one example of finding eigenvalues and eigenvectors. This remark will be helpful in finding out solution of characteristic equations in calculating eigenvalues and eigenvectors. So we consider this matrix. We want to find out eigenvalues and eigenvectors of this matrix. So the first step is to write down the characteristic equation. We denote given matrix by capital A, and as we know, the characteristic equation of A is determinant of A minus lambda I equal to 0, where this capital I is a identity matrix of order 3 because given matrix is of order 3. Now to write down this determinant, as we discussed in the previous lecture, we subtract lambda from the main diagonal and we keep other entries as it is. So we subtract lambda from the main diagonal, 4 minus lambda, 1 minus lambda, 1 minus lambda, and we keep other entries as it is. Now we know how to find out determinant of square matrix. We expand with the first row, positive, negative, positive. So 4 minus lambda into determinant of this matrix, which is 1 minus lambda square minus 0. Minus 0 into determinant of minus 2 0 minus 2 1 minus lambda, but it is 0, plus 1 into determinant of this matrix minus 2 1 minus lambda minus 2 0, which is 0 minus minus plus 2 into 1 minus lambda equal to 0. This we rewrite in this way. Now in these two terms 1 minus lambda is common factor, so we can take it outside. So here we have 4 minus lambda into 1 minus lambda plus 2. Now we multiply 4 minus lambda and 1 minus lambda and we obtain this lambda square minus 5 lambda plus 6 equal to 0. So 1 minus lambda is 0, lambda square minus 5 lambda plus 6 equal to 0. This can be easily factored. We can rewrite minus 5 lambda as minus 3 lambda minus 2 lambda, and here we take lambda common, so here in the bracket lambda minus 3, and from these two terms we take minus 2 common, so we have lambda minus 3, and again we take lambda minus 3 common, so we obtain lambda minus 3 into lambda minus 2 equal to 0. So therefore the eigenvalues of given matrix are lambda equal to 1, 2, 3. So we have 3 different eigenvalues. Now we find out eigenvectors corresponding to each eigenvalue. So we assume that this x equal to x1, x2, x3 is an eigenvector of given matrix A corresponding to eigenvalue lambda. Therefore we must have this system A minus lambda I x equal to 0. This system must have infinite number of solutions, or it must have non-trivial solutions. Now here we write down square matrix A minus lambda I, which we have written here, so that we write here x is x1, x2, x3, and right hand side is 0 matrix of order 3 by 1. Now we multiply these two matrices, first row into first column, that is 4 minus lambda into x1 plus 0 into x2 plus 1 into x3, that is x3, and we equate simultaneously, so that is equal to 0. Similarly second row into first column, minus 2 into x1 plus 1 minus lambda into x2 plus 0 into x3 equal to 0. Then third row into first column, minus 2 into x1, 0 into x2 plus 1 minus lambda into x3 equal to 0. So this system we have written in this form. Here lambda is an eigenvalue and this x1, x2, x3 are unknowns. They are the components of eigenvector x. Now we solve this system 1 for different values of lambda. So there are 3 eigenvalues here. So for each eigenvalue we have to solve this system. So first we solve this system for lambda equal to 1. So if we put lambda equal to 1 here, we have 4 minus 1, which is 3x1 plus x3 equal to 0. For lambda equal to 1, these two terms will be 0. So we have minus 2x1 equal to 0. And this implies x1 is 0. And from equation 1 we can write x3 equal to 0 because x1 is 0. So if we put x1 0 here, we obtain x3 equal to 0, and we don't obtain any restriction on x2. So x2 is arbitrary, we can have any value for x2. So hence we can write our eigenvector as x1 and x3 are 0. We keep x2 as it is. X2 is any real number. We can take x2 outside, or this this vector can be written as multiple of x2 in this way. x2 is outside and here 0 1 0, and x2 is any real number. So these are the eigenvectors corresponding to eigenvalue lambda equal to 1. For different values of x2, we will have different non-zero eigenvectors for lambda equal to 1. This eigenvector 0, 1, 0 is linearly independent eigenvector corresponding to eigenvalue lambda equal to 1. All the eigenvectors are scalar multiple of these linearly independent eigenvectors. So for different values of x2, we will have different eigenvectors. So we can write that x equal to x2 times 0, 1, 0, where x2 is any real number, are eigenvectors of given matrix corresponding to eigenvalue lambda equal to 1. If we wish, we can assume x2 equal to some parameters, say t, and we can write in this form also: t times 0, 1, 0, where t belongs to R is parameter. So some authors write in this way also. They assume this arbitrary x2 equal to some parameter and they write eigenvectors in this form. So that is also correct, but it is enough if we are writing in this form also. So these are the eigenvectors corresponding to lambda equal to 1. Now we put lambda equal to 2 in the given system and we solve the corresponding system. So for lambda equal to 2, here we have, if we put lambda equal to 2, first equation is 2x1 plus x3 equal to 0. Second equation is minus 2x1 minus x2 equal to 0. And third equation is minus 2x1 minus x3 equal to 0. So that we have written here. So if we take negative sign common from the last equation, then equation 1 and 3 are exactly same, 2x1 plus x3 equal to 0. And if we take negative sign common here, we have 2x1 plus x2 equal to 0. So we can represent x2 and x3 in terms of x1. So x3 can be written as minus 2x1, x2 can be written as minus 2x1, and there is no restriction on this x1. So x1 is any real number, it is arbitrary. So therefore x equal to x1, x2, x3 equal to, we replace x3 and x2 by minus 2x1. And then we write this as x1 times 1 minus 2 minus 2, and x1 is any real number. So these are the eigenvectors corresponding to eigenvalue lambda equal to 2. 1 minus 2 is linearly independent eigenvector corresponding to lambda equal to 2, and all the eigenvectors are scalar multiple of this linearly independent eigenvector 1, minus 2 and minus 2. Similarly, we can find out eigenvectors corresponding to lambda equal to 3. If we put lambda equal to 3 in the system 1, we can see we have 4 minus 3, which is x1 plus x3 equal to 0. If we put lambda equal to 3 here we will have minus 2x2. So it is minus 2x1 minus 2x2 equal to 0. And last equation is minus 2x1 minus 2x3 equal to 0. So after putting lambda equal to 3 in system 1, we obtain these 3 equations, and from these 2 equations we can take minus 2 common. So we will have x1 plus x2 equal to 0 and x1 plus x3 equal to 0. And again we can write x3 and x2 in terms of x1, and x1 is arbitrary, we can take any value for x1. So therefore x equal to x1, x2, x3, we replace x2 and x3 by minus x1, and after taking x1 outside we have 1 minus 1 minus 1. So this 1 minus 1 minus 1 is linearly independent eigenvector corresponding to eigenvalue lambda equal to 3, and all the eigenvectors are multiples of this eigenvector corresponding to lambda equal to 3. So these are the eigenvectors of given matrix corresponding to lambda equal to 3. Now in this example we are able to solve the systems corresponding to different eigenvalues directly, because we have these simple equations. So we can represent two variables in terms of one variable, but sometimes these systems will not be directly will not be like that, like this system, so that we can solve them directly like this problem. So if we are not able to solve the given system directly, we can apply either Gauss elimination or Gauss-Jordan elimination method. So we will discuss that type of examples in the next lecture. And this is all about today's lecture. In this lecture we have discussed how to find out eigenvalues and eigenvectors of a given matrix. So I hope you like this lecture. Thank you very much.